He's now with Royal Haskoning, serving as a senior consultant in urban drainage and wastewater treatment. And since 2010, he's also associate professor at Delft University of Technology in the Department of Civil Engineering and Geosciences. He's member of the International Water Association that is hosting this conference, and in the Committee of Urban Drainage and in the Secretary of the IWA Sewer System and Processing Working Group. So thank you for attending, and the mic to you.
Yeah, thank you very much. I have to thank the previous speakers because they already introduced the topic, so I can stick to my own case study, which builds on the results of a very large project we had the last few years in the Netherlands at Waterboard de Dommel, where Stefan Weijers is also from, the Calista project, where we did an integrated approach to come to a cost-effective solution for the system. And I'll explain later why we had to do this. And I'm presenting this paper also on behalf of the co-authors listed there. In this short presentation, I'll introduce the case of Eindhoven, the Eindhoven system, how we built an integrated model, the monitoring data required to validate and calibrate this model, and some issues that were there to be able to finally totally calibrate this integrated model. And that's where data mining was necessary to get all the information from the available data. And I'll show you also some issues that are related to the scale of the system, and finally come to some conclusions. This is the system of Eindhoven. You have this, the river Dommel comes from the south, from Belgium, and then flows toward the river Meuse in the north. And it's a rather small river with only a base flow of, let's say, 1.5 cubic meters a second, so it's not that big. And in the red part, you have the city of Eindhoven, that's over here. And in the city of Eindhoven, you have a very large treatment plant for 750,000 inhabitants, and that has a maximum hydraulic flow of almost 10 cubic meters a second. So you can imagine that there's, if that one spills at the maximum rate, and you have this small base flow, that you could exert some water quality problems in the receiving water. And apart from the treatment plant, we have 10 municipalities, mostly with combined sewers, and over the whole area we have 200 CSOs that also discharge to this river. So the river receives the water from 200 CSOs and the treatment plant, and as such it is heavy loaded due to the urban environment. And this, of course, gives some problems. One of the problems is shown here. During a typical week in the Dutch summer, the Dutch summer always has this rain like today, but then the showers are a bit more intense, and if they're a bit more intense, then you have a water quality impact on the receiving water. And what this chart shows you is on the right axis the CSO discharge in cubic meters an hour, so it ends up with approximately 80,000 cubic meters an hour. That's quite some water. And on the other axis you can see the DO concentration in the river. Now, before this storm event it was nice and warm, and then you have DO concentration of, depending where in the river you are, between 5 and 7, which is okay. Then you have a first strong CSO event, and then you see bang, the DO concentration goes down, and it doesn't go up soon, but it takes about a week to recover. And if you then have another serious storm event, and then another, then in the end you end up with concentrations in the river of about 1 to 2 milligrams of DO, which is not good for the for the fish and the other ecology. So based on this, you could already say that ecology here is an issue. Another thing that we have in this area is, of course, this very large treatment plant. And what you would see during a storm event is that the ammonia concentration in the effluent plant goes up. And this data is 24-hour data from a sampling apparatus upstream of the treatment plant in the river and downstream. So this is the upstream one, where you have rather low ammonia concentrations. It goes up a little bit during a CSO, but only to, let's say, 1 to 1.5 milligrams a liter. And this is what you have downstream of the treatment plant, where you can have ammonia concentration of up to 9-10 in the receiving water, which is far above the standards that you would have to sustain a good ecological quality. And that's why the project Calista was there, to see how can we minimize investments to be able to cope with these tremendous peak loadings to the receiving waters. And in order to be able to answer that question, you need to go modeling, to do some scenario studies, and that's what's the focus of today. So we have this sewer system with 200 CSOs, 10 municipalities, kilometers of sewers. We have this very large treatment plant, and we have the receiving waters, and that all needs to be combined into one integrated model. And that's where the problem starts, because you can build this model, but then you need to validate it. And in order to validate it, you need to compare the outcome of the model to monitoring data. And if you have this very large integrated model, the only input that you would have in the end is rain, the rain event. That you put that as an input, then the CSO starts running, then the influent comes at the treatment plant, and that in the end has an impact on the receiving waters where you measure DO and ammonia. But if you only measure DO and ammonia in the river and you put this on your model, you will not be able to identify places where your model is wrong. If you have this very large model, you cannot identify the errors in the model. So what you need to do, in fact, is first calibrate the submodels, then integrate it into a total model, and then see how it's working. So that's what we did, in fact. And therefore, we were happy that there was a monitoring network. You said large monitoring networks are expensive. Now, we built them here because just building measures is also very expensive. So in this area, this is a map of the area, and each red dot is a monitoring location for a CSO where a level sensor was placed, which gives you the duration of the events and also an approximation of the CSO volumes. So that's there at the sewer, which gives you the opportunity to calibrate the sewer model to get combined with all the monitoring data of the pumping stations. In addition, we have this monitoring at this very large treatment plant, which is fully equipped with monitoring sensors. I'm not going into detail for that, but the influent is measured, all the relevant process dynamics are measured, and also the effluent is measured and monitored. So there's a lot of data available for this treatment plant. Where I have to point that all the process data and the effluent data, that's on a continuous basis, and that's data that you need to drive this plant. We also have, let's say, UV fish sensors at the influent and ammonia sensors of the influent. Those are not yet used for the control of the plant, and those are the ones also with having these issues with data quality associated with them. And then we also have monitoring located in the river. So we have DO sensors in the river, flow sensors, ammonia sensors, and also periodic sampling, as well as ecological sampling to get an idea about the ecological quality. And the ecological quality is rather good in the south, where it's not affected by the CSO than the treatment plant. And as soon as it passes by the city of Eindhoven and the treatment plant, then you don't meet the Water Framework Directive requirements anymore. So something needs to be done there. And then you have this very large monitoring network, and like the previous speaker said, the sensors do not always operate fine. So first you need to apply data validation, and there's a lot of people working it. I think Geert van Mil is also here. He's working on this CSO locations to have this 200 CSO locations up and running. And then you can make some charts about the results of this data validation that we applied. And you see that in the beginning you have to get used to the network and it starts running. And then we have a data availability of, let's say, approximately 90% of good data, which is sufficient, which means that 90% of all data points are there and are good. Here you see a drop in the availability of good data. That was because then we added some new data validation techniques for linear trends. And then in the first place, a lot of data was saying, oh, it's tricky data, we have to check later. And after the check of Geert van Mil, it was proven that most of this data was good. And we have here a monitoring network that performs pretty well with, let's say, 90% of data availability over a long period. And that's for this 200 sensors, which is quite okay. So we have a lot of data there. But we do not have, of course, 100%. And this 100% is what you would need if you want to have data on all CSOs, and which you would need if you want to calibrate the model very well. This chart shows you the availability of a couple of sensors for one municipality. So each line is the availability. If it's green, you have it. If it's orange, it's doubtful. If it's red, you don't have it. And it's not good. And if it's white, it's lacking. And what you see is that there are some periods in time when all sensors work, whereas many periods in time when you don't have all the data available. And that's an issue, because if you want to feed your models with, if you want, for example, to feed the receiving water model with the flows from the CSOs, and you don't have all monitoring locations available, you cannot run the simulation because you lack data, and that's where this data mining was necessary. And of course the data validation is just how to keep up with these 200 sensors at a time in the CSOs and also at the treatment plant. It's quite a lot of work. But after all, we have a lot of data, and of course we have the issue of data availability. And in the beginning we decided that we're going to calibrate the submodels, the sewer, the treatment plant and the receiving water, and we were checking for what period in time we had good data available to validate the model. And then we decided that the river model was most important because that the receiving water quality was the main issue. And we had only, at the time that we were doing the study, data available for 2010. So we decided, okay, we're going to calibrate the receiving water model for 2010. But for that period, we did not have good data for the sewer system. So we were not able to generate input for the receiving water model. And the wastewater treatment plant model was calibrated based on 2007-2008 data when we had real good influent data. So what we had here was 3 systems where we can calibrate the model, but for different periods in time. And when you need to combine them, then infect your data mining, and you use in fact the sewer model as a software sensor. So what we in fact did was first calibrate the sewer model for the period of 2011, and once the model was good enough, we put the precipitation of 2010 on this model, and then that model generated the input for the receiving water model. So it's quite a hassle to get the data for this integrated model. And we had to combine also many monitoring networks. I showed you the new monitoring networks for the CSO, but that was only available from 2010-2011. And we also calibrated the models using all the period in time. So you need to combine a lot of databases from municipalities to be able to do this work. In the paper on table 2, I listed all the data that we used to be able to calibrate the sewer model for Eindhoven. That's a tricky one, this. Then some results. In the end, we were able to simulate the river model, the receiving water model, and we were quite happy that it had at least mimics the dynamics of the river. What you see here on the low axis is the flow from the treatment plant. So the black line is the effluent from the treatment plant. These blue spikes are the CSO volumes also, and the CSO volumes are based on simulated values because we did not have monitoring data at that time. The effluent data is based on monitoring data, and all these black dots here is measured DO in the river. And the red line is the measured DO, or let's say the model DO for the receiving water model. And you can see that at least the dynamics are pretty much okay. And for this type of model with 200 CSOs and 1 treatment plant, this is fairly okay. So we were quite happy to have this. The river model was quite okay having these other inputs. And then we switched to the totally integrated model where we only use precipitation as an input. And then we got this picture. And if you recall the previous one, you can see that here the dynamics are a bit off. Here we don't seem to have an event at all. And here it's also a bit off. And if you remember the previous slide, there was a CSO event there modeled. And for this particular case, it wasn't there. And this showed another issue that we are starting to work on when you use these integrated models. What you in fact do is you make a simple reservoir model for the sewer system, and with that you just throw away all the geographical information on the extent of the sewer. The spatial discretization is gone. And for this simulation, we also used only 1 rain gauge because the sewer model is only 1 reservoir, so you can also use only 1 rain gauge there. And this graph shows you that there we just threw away too much information about the spatial distribution of the precipitation and also about the spatial distribution of the performance of the sewer system, because the integrated model simply did not see this CSO because it wasn't in the input of that particular rain gauge. So there's a scale issue there. If you have these very large integrated models, you have to select your model input very properly. But yeah, as soon as you simplified your model a bit too far, you're not able to mimic this anymore. So this is describing somewhere the limits of this integrated approach using only 1 rain gauge. And to conclude, finally, I think the calibration of integrated models can be done properly, but it also demands, and that's often overlooked. If you look in the literature, people say, "Oh, I calibrated the integrated model, but you need a tremendous amount of data to be able to do so, and that's often not the case. So you have to question, if you read this in a paper, that the integrated model is calibrated, how is it done? Because you need a tremendous amount of data. And as that is the case, data mining helps, and especially to use a model as a software sensor to transform knowledge from one period in time to another. In order to be able to improve this model. And one issue, and we need to work on that a bit further, of course, for integrated models that cover a large area, the spatial discretization is very important, not only of your model, but also of your precipitation input data. And that's a lesson learned, which is, I think, relevant for more integrated approaches. Thank you for your attention.
We have some time for questions.
Winkler from Vienna University of Technology. I mean, just for comparison purposes, did you ever try stuff like grey box or black box models to model the DO from, I don't know, rain gauges or rain amounts, that you just have a
directly model the
just a black box or grey box model?
We just have linear reservoir models which are computationally not that demanding, so we were happy to have that. In fact, a new PhD student, Petra van Daal, in the group in Delft, she will be working on how detailed the model should be to be able to predict the river quality. And in the end, she might come up with the solution you propose here. Yeah.
I don't want to say it. I mean, there is a lot of system understanding that you can get from an integrated model, but stuff like the OO often goes more easy.
Yeah.
Luis Colominas from ICRA. Do you have also data on ammonia? Because you show data on DO, and it is more difficult to adjust ammonia, or
no? It's much easier.
It's much easier.
It's much easier because the ammonia is just dilution, and the ammonia also doesn't stay long in the system. It's just if you have the flow right, you're okay. And the treatment plant model is very good in predicting the ammonia concentration. So ammonia is not an issue. It was the DO, and in fact, the biggest issue here was to mimic this delay in DO consumption, because the river flows and the retention time hydraulically is only 1 day. So you can expect that after 1 day the problem is solved, because then you have clean water from Belgium. But that isn't the case. We have this sediment that settles after the CSO, and then you have this slow consumption of DO, and that lasts for about a week, and then it's gone. But in that week you have a problem. Yeah.
Good.
Cool.
Hi. The data that you're collecting, how is that connecting to the decision makers in organizations? I imagine there's a lot of information that can be derived to do more decision making at the top level.
Yeah, this data is used at various levels. At first, the data was used to determine how big the problem was in the receiving waters. Because before the project, we did not have this continuous data, and the project means before 2006. There was some feeling that there was something wrong with the receiving water quality, but it wasn't clear. So the first added value of having all this data is to be able to clearly define, okay, we have low DO for this periods, we have high ammonia peaks. And if I may recall, these high ammonia peaks, they are not in the receiving water standards in the Netherlands. We have requirements for N total, P total, but not for ammonia for a short period in time. So it isn't there. The water boards, they don't focus at ammonia concentration in receiving waters because it's not in the requirements. So the data itself showed that there was a problem, and the second step that we also use the monitoring data to define standards for ammonia, and then we also used it to build this model, and this model has then also been used already to determine a first set of measures that can be effective, and the measures that will be implemented soon, as the no-regret measures are real-time control, to make better use of the treatment capacity and the capacity in the large transport sewer, and it will be aeration of the river. So the river will actually be aerated to get rid of all this DO depletion. So there's a lot of things already done with the data, and there will be much more in the future. Yeah.
Any other question? Otherwise, I have one, which is probably a little bit naive. Can you go back to the slide where you showed that oversimplification of the model that led to, let's say, that was it. When you showed the oversimplification of the model that led, let's say, to incapacity of... the question is, what would be the criterion that you would apply in order to remediate this oversimplification? How you would break down the model of the system that here oversimplifies it on a spatial basis or on a functional basis?
Yeah. It's not easy in this case because this particular CSO event only occurred in the city of Eindhoven, which is a city of 2,000 hectares, and which is one large combined sewer district. So it's all free-flowing towards the treatment plant, and it has 24 CSOs. And it's not very easy to cut this system in small pieces if you want to have a simplified model. So we were doing quite well by having this model. First we calibrated the hydrodynamic model, which is okay. We have also had the simplified model. But then you have the issue of which rain gauge to use and how to put rain information onto it. I think it will be that we will be calculating a net rainfall for this catchment. So use rainfall radar data for the catchment that we have, and then come to a net average rainfall for this catchment, and then the prediction will be much better than use only one rain gauge. So the solution won't be in the model, but in the input, in this case. Yeah.
Thank you. I think that you're perfectly on time. So thank you for attending the session, and see you this afternoon for the continuation of the program.